Okay, so we are about to begin chapter 8, and chapter 8 is about factoring. And so we talked a little bit about this last week when I was kind of like alluding to what we were going to be talking about. Basically, what we're doing is we're taking what we did in chapter 7 and we're doing it backwards. So for example, when you did problems like x plus 4 times x minus 3, and you did the box method, you ended up, or just distributed. So either one is fine. And you end up finding out that this is x squared plus 4 minus 3 would be plus 1x minus 12. Basically what we're doing right now, or what we're getting to, is I'm going to give you this, and I'm going to ask you what were the two binomials that you multiplied that would give you this answer. Okay, so we're working backwards, and that's called factoring. So we're going to start really, really basic, because this is pretty much like, this is the culmination of what we're going to do. What does culmination mean?
Say combination.
Culmination. Like, you know when you write a paper for comp, or whatever class you write papers in, composition, and you start with, like, you write a thesis, and then you do an outline, and then the end product is like the whole paper. So the culmination is your final paper. When I say culmination, what I mean is we're going to do a bunch of little stuff, and it's going to build up to this. Okay, so we don't need to worry about this right now. We're going to start with, in general, what basic factoring is. So a factor is the whole numbers, or sometimes variables, that are multiplied to get a product. So for example, in the problem 3 times 4 equals 12, 3 and 4 are the factors, and 12 is the product. The product is the answer to any multiplication problem. Are there any other ways you can break down 12? Yeah, Ali? 6 times 2. That will be another set of factors. Anything else? Montreal?
12 times.
Yeah, 12 times 1. Are there any others? 4 times 3, so you could flip them. You could flip the order. All right. You could also do like -3 times -4, but since we're talking about whole number factors, we're only going to talk about the positive ones. All right. Essentially, keep in mind you could add in all the negatives if you wanted to. You would just have to make them both negative. But when we're talking about factors, we're talking about what can we break a number down into. And when we talk about breaking it down, we mean what can multiply to give you that number. All right. So factors are basically what number you can multiply to give you that number. What is always a factor of everything? 1. 1 is always a factor. So 1 times whatever the number is itself is always a pair of factors, which means that the fewest number of factors a number can have is 2. Does anybody know what a number is called if it has only 2 factors? What's a number called if it has only 2 factors? So if only 2 numbers go into it. Diego? A prime number. Okay? So a prime number is a number with only 2 factors, whereas 12 has 6 factors. 1, 2, 3, 4, 6, and 12. All right, so 12 has a lot of factors. Okay, so which of these, I'll move it up a little bit, which of these is a prime number? 7? 2? 29? Why not 15? Okay, 5 times 3 can also give you 15. 12 we just looked at. 12 has a lot of factors. But the only thing you can multiply to give you 2 is what? 2 times 1. The only thing you can multiply to give you 7? 7 times 1. And 29 is 29 times 1. Okay, so those are prime numbers. Whereas 15 and 12 are called, does anybody know what they're called when they're not prime? Composite, exactly. Composite numbers. Why do you think they call them composite numbers? Maybe it's compatible. What does it mean to be composed of? To be made of. So it's made of a bunch of factors. Composite means it's like a bunch of different things. There's something called like composite wood, which is basically like, have you ever seen plywood? Yeah. Looks like tons of different wood. They just press it into a sheet. So composite means a bunch of pieces put together. So 15 and 12 are composite numbers because you can do a lot of different pieces to get 15 or 12. More to get 12, obviously. All right? What number is the only even prime number? 2. How come every other even number is not prime? Okay, what? What goes into every other even number? 2. 2 goes into all the even numbers, right? So you know 1 goes into it, you know itself, and you know at least 2 goes into all the even numbers. Okay, good. What about 1? Is 1 prime or composite? It's neutral. Why? Why is it not either one? It's neither prime nor composite. How many factors does a prime number have? 2, right? How many factors does a composite number have? Any number, so more than 2, okay? How many factors does 1 have? Just 1, just itself. So that's not a prime or a composite, okay? What about 0?
0 is 0. It's a prime. Or prime because actually it's neither.
Neither? Okay. I would say probably neither, but what can you multiply times 0 to get 0? Anything. So really it's like you could consider it both. We don't consider it anything. 1 and 0 are kind of, you wouldn't file them under either prime or composite. Okay. So how many of you guys have seen these before? Sometimes you call them factor trees, prime factorization. What's happening up here? You're breaking the number down into what? The simplest form. And simplest form means that everything here, all the ones that are circled, are what kind of numbers? Prime numbers. So this is called the prime factorization. You keep breaking it down until you get to all prime numbers. All right, so for instance, let's take a look at another one. Give me a 3-digit number. 3-digit number. 325. Okay, how would I start this? How would I start my prime factorization here? Brendan?
First you have to see if 325 is a prime number.
Okay, so first I need to know if it's prime or composite. Is this prime or composite? It's composite. It's a composite number. First of all, anything big is usually composite because the bigger you get, the more likely it is something goes into it. But we also know it's composite because it ends in a what? 5. Which means what goes into it for sure? 5. You know definitely 5 goes into it. So then the first step is to break this down into some multiplication problem. It's probably not going to be prime yet, but we're going to start here. So what do you guys think goes into this? 25 times something, right? So 25... And the way I always think of when I'm dividing by 25 is if this were dollars, how many quarters would that be? So how many quarters would you need to make $3.25? That would be $2.25. 13, because $3 would be 12, and then another 25 cents would be 13. Okay, so 13. Now, ask yourself, are either of these prime? 13 is a prime number, so I'm going to circle it, because that means we're done with this one. We don't need to keep going. Except 25 is not prime, so what do I have to do there? Break it down, and that gives me 5 times 5. Are either of those prime? Both. So I circle those, and then I'm done, except the actual answer looks like this. 5 times 5 times 13, or 5 squared times 13. All right, so here is our prime factorization. This is the factor tree. Prime factorization is the actual product, so the actual multiplication. So if I ask you for the prime factorization, you have to put this part, okay? It's not enough just to do the factor tree. That's the hard part, okay? But until you put it in the actual product, it's not a prime factorization. So make sure if you're doing all the hard stuff, which is the factor tree, that you write down your answer. Okay, so prime factorization is factor trees you've seen before. How many, what are some ways that you can break down really big numbers? Like we said, this one ends in 5, so you know what goes into it. 5. What if they end in 0? 5 and 10 both go into it. If it ends in 2, 4, 6, or 8, you know that 2 goes into it. Okay, so work from there when you're trying to figure out what are the factors. And you guys will have calculators, so you can always do it. If it's a really huge number, something like 4,026 or something like that, if it's an even number, I pretty much always just start dividing it by 2. All right, so I divide it by 2, and then that gives me 2013. And then I have to look at that and say, what am I going to do next? And so then I get out my calculator and I just plug some stuff in and try it, okay? So prime factorization, again, is not done until you get right here. Okay, so who can come try this one? Who can come try this one? 75. Diego? Oh, don't put your pen down. You're not done. Good. 3 times 5 squared. Perfect. All right. How can you tell if you're right? If you go back and check this, this should give you what? 75. Could we have done this a different way? Yeah? What else could 75 break into? 5 times 15. And then this is prime, and this breaks down to what? 3, 5. So what do you notice? You still get the same answer, okay? If you're doing prime factorization right, no matter what steps you take, you should ultimately always get to the same answer. So even if you and your neighbor do it with a different number at the beginning, you should still always get to the same number. Okay, go do these 6 at your boards if you can. So when we're finding the prime factorization of things, the reason that we're reviewing this right now, because most of you have probably done this or something like it before, the reason that we're reviewing it is because it can help us find greatest common factors. So we're going to talk about how to do that right now. So before we start that, what is a greatest common factor, often abbreviated GCF? What is a greatest common factor? Brendan?
The lowest to something multiplied by?
That will be a least common multiple. It's the largest factor that goes into 2 or more things, right? So for example, if I have a list right here of 24, 36, and 48, and I want to know the GCF of those, I want to know the biggest number that goes into 24, 36, and 48. And most commonly, you guys have used this in the past to reduce fractions, but today we're going to use it, and in the future we're going to use it to factor polynomials and use those to kind of make things simpler for ourselves. So looking at this set of numbers, 24, 36, 48, does anybody know off the top of their heads right away what the biggest factor is? Probably 12, right? 12 goes into all of those, but we want to confirm that it's the biggest. So we've got 2 ways to do that. We can either make a list of all the factors, all right, or we can use the prime factorization. Both of those are good ways. Sometimes one is more efficient than the other. So let's look at making a list. So let's say to make a list, we start with 24, 36, and 48. And we've got to make a list of all the factors. So what goes into 24? What always goes into everything? So we start with 1. What else? 2. Just 3? What about 4? 5? 6? 7? 8? 9? 10? 11? 12? 12? And 24. All right, so those are all of our factors. 30, what? Well, hey, that's the highest factor for 24, yes. So the biggest factor of 24 is 24. But we're looking for the greatest common factor, which means the one that's going to be in common with all of them. So 36.
I already have it.
Okay. Can you hold that thought? We're going to do this. 18 and 36. The way that I do it is you match up the pairs kind of in your head. So 1 times 36, 2 times 18, 3 times 12, 4 times 9, and then 6 times itself. So if you're ever like, I'm not sure if these go into it, just make sure it matches up with one of the factor pairs. Okay, 48. 1, 2, 3 does, 4 does, 5 doesn't, 6 does, 7 doesn't, but 8 does. And since these two multiply by each other to get 48, now we know we're kind of working down. So how many times does 4 go into 48?
12.
How many times does 3 go into it? 16. And 2 is 24. And then 48. Okay, so here are our lists. And now how do we find the greatest common factor? See which one is in all of them. The biggest one that's in all of them, which happens to be 12. Which Brendan told us from the beginning that was our GCF, right? Okay, is this efficient? Sort of, like it can be, particularly if your numbers are smaller and you know all the factors off the top of your head. But if I asked you what the GCF of 925 and 365 was, do you know all the factors of those off the top of your head? No? So then taking a list and making a list of those is going to take forever. So we're going to talk about how to use greatest or prime factorization to find greatest common factor. Can you put your phone away, please? Thank you. Okay, so 24, 36, 48. I want to do the prime factorization of each of these. So 24 breaks down to what? 12 times 2. And this is prime. 12 breaks down to 4 times 3. This is prime. And then this breaks down to 2 times 2. All right, so then the prime factorization of 24 is 2 times 2 times 2 times 3. All right, I'm going to hold that thought right there. All right, what about 36? 12 and 3? So now 36 is 2 times 2 times 3 times 3. And last but not least, 48 is what? 12 times 4. I don't know, I just always do 4 and 3. I don't know why. All right, so that's 4 2s and a 3, right? So 48 is 2, 2, 2, 2, 3. Okay, now, from here, what you can do is you find all the ones they have in common, all right? So they each have 1 2, right? Do they each have at least one more 2? Yes? Do they each have one more 2? No, 36 doesn't, so that's all the 2s. And then do they each have at least 1 3? Yes? So here are the numbers in common. So then you just multiply those. 2 times 2 is, 4 times 3 is 12. So that's your GCF. Okay, you only multiply it once. You don't do all of them, because then that would be a huge number, bigger than all of them. Okay, so to find your GCF by prime factorization, you do the prime factorization, you circle the common ones, and then you multiply them. All right, I'm going to write those steps out. You don't need to write them down, but they'll be posted. All right, so first things first, do the prime factorization. Second, circle all common factors. And then 3, multiply 1 set. All right, so multiply 1 set of those. Is it still a lot of work? Yes, it's not easy, right? Or it's not necessarily, I don't want to say not easy. There is a lot of work involved, but it's something that you can do pretty simply. The process is the same for all of it. So this helps you find a greatest common factor, particularly for those numbers that you don't know off the top of your head. Now, could you have figured out 12 off the top of your head without doing any of this? Yes, by all means you could have. So if you know how to do it, like if you know what it is right away, then don't waste your time doing this, all right, if you know that it's 12. The problem is sometimes you get a common factor, but not the greatest one if you don't break it down. Okay, so how would I find the greatest common factor of something like 12y to the third and 18y to the fourth? So this is a monomial and this is a monomial, and I want to know the biggest thing that goes into both of them. So what do you think I have to do? What do you think, Brendan? What do you mean square it?
You have to turn it into
A whole number?
yeah, 12 times 3 squared. 12 times 3 squared. 12 third. 12 to the third power.
It's not 12 to the third power, though. It's 12 times y to the third power. So y is to the third, but the 12 is not. Is that what you're saying? Like try to get rid of the exponents? This exponent doesn't go with the 12, so you can't do that. Okay? It would be if it were in parentheses, but it's not. So I'm looking for the greatest common factor of those two things. Remember, greatest common factor is what? Largest factor that both things have in common, right? So in this case, we're looking for the largest that 12 and 18 have in common, and also y3 and y4 have in common. So we look at it separately. So what's the biggest thing that 12 and 18 have in common? 6. So 6 is the GCF of the coefficients. So that means 6 is our GCF here. All right, what about y3, y4? They have y in common. How many y's? How many y's does this have? How many y's does this have? So how many do they have in common? 3. All right? So y3 would be our variable part of the GCF. So then our whole GCF would be 6y to the third. Okay? Because they both have 6 in common, and then they both have at least 3y. So the shortcut way of doing that is to say the smallest exponent of whatever the common variables are. Okay, so the smallest exponent of the common variables is 3. So that means our GCF would be 6y to the third. Okay, so let's do one more of these. All right, what do you think the GCF would be of these two? Let's look at the coefficient first. What's the GCF of 28 and 14? 14. 14 goes into both of them. So that means our GCF has a coefficient of 14. All right, and then do they have common variables? Yes? What? How many? 2. Why 2 and not 4? Yeah, they at least both have 2. So your common would be x squared. Okay, one more. All right, what do you think the GCF would be here?
12.
Okay, 12 is the number, because 12 goes into both of those. What about the variables?
They don't cancel out. You just leave them at that.
Okay, so do I put them both in the GCF?
Yeah.
Do they both have both of them? Remember, they have to have in common. The C stands for greatest common factor. Do they both have y's? Do they both have x's? So then your GCF has no variables. They have nothing in common for variables, so it's just 12. Okay, so GCF is only the common stuff. So common means they both have it. So if it doesn't both have a variable, then you wouldn't have anything in common. Okay, all right, so I want you to do 3 of them. Pick any 3 that you want to do.